Hello, everyone. So last time we were looking at the concept of limits and how to compute limits. This time, laws. We looked at laws or rules for computing limits. So we provided a list, for example, limit of a polynomial function. We saw that for a polynomial function, we can simply replace x with the number. Or other rules, for example, for rational functions, or if you want to find the limit of addition of two functions, what should we do? So one thing we haven't looked at it yet, so is basically the limit of a trigonometric functions. So the limit of trigonometric functions. So theorem, and let f of x equals sine x. Then, so this is part one. Then we can set limit sine x as x approaches to a is equal to sine a for any real number a So sine function is also a very nice function in the sense that, when you want to calculate the limit, similar to polynomials, that when you want to calculate the limit, you can just simply replace x with the number. Same thing for sine function. To calculate the limit at a, you can just simply replace x with a. And similarly for cosine function, limit cos x as x approaches to a is equal to cos a. For tan function, so limit tan x as x approaches to a is equal to tan a if a belongs to the domain of tan x, i.e. if cos a is not equal to 0. Okay, so for sine a, limit sine x and cos x at a, there is no restriction for a. So for any real number a, you can just simply replace x with a. Same thing for cos x. For any real number a, this is valid. But for tan x, we can replace x with a as long as a is in the domain of tan x. And similarly for cot x, as x approaches to a is equal to cot a if a belongs to domain of cot x, i.e. if sine a is not equal to 0. Remember, tan x means sine x over cos x. So for tan, we can say that a is in domain if denominator is not 0. Denominator not 0 means cos a not 0. For cot x, we still should require denominator to be non-zero. And in that case, it means sine a must be non-zero. And so, for example, let's say if you want to find limit sine x as x approaches to pi over 6, let's say. So according to the property 1 above, we can write this one as sine pi over 6, which is 1/2. Yeah. Okay, so for finding limit sine x approaches to a, just replace x with a. What about, okay, so for sine x, cos x, tan x, cot x, everything's straightforward. What about, let's say, for example, sine 2x or sine 2x plus 1, something like that. So in that case, we need to look at the composition of two functions. Okay, so for composition of two functions later, we will see, we'll provide a theorem about continuity. That, you know, for composition of two functions, again, as long as they are nice functions, we can say that for the composition of two functions, to calculate the limit, we can just replace x with a. Okay, so this one for composition of functions, I'll state later using continuity, because if I want to state it now, it's going to be a little bit complicated. With continuity, once we know the concept of continuity, we can mention that theorem very neatly. Okay, but so for now, let's just focus on sin x, cos x, tan x, cot x, or these functions times another function, or addition of these functions with another function. So for composition, like I said, you know, again, everything will be as long as the functions are nice, such as trigonometric, exponential, rational function, etc. Again, you can still just replace x with the number, but I'll state the theorem formally later after we learn about continuity. So for now, so we learned about sin x, cos x, tan x, cot x. So let's give another example. Let's say limit tan x as x approaches to pi over 6. Again, by theorem part 3, we can say that this is tan pi over 6, which is 1 over root 3. What about if, let's say, limit tan x approaches to pi half, let's say from right. So the theorem part 3 is valid as long as a is in domain of tan x, but pi half is not in the domain of tan x because tan pi half is undefined. So we cannot use the theorem. Instead, what can we do? So this one, tan x, we know it's sin x over cos x as x approaches to pi half from right. So then this is sin pi half divided by cos pi half from right, which is 1 over, okay, what is cos pi half plus? So let me draw the unit circle. Remember last time we established that if we have, for example, cos pi half plus and cos pi half is 0, it does not mean that cos pi half plus is 0 plus. Because this plus here just means x is a little bit bigger than pi half. So there is really no implication about whether the answer is 0 plus or 0 minus unless we can verify or analyze the situation. But only from the fact that there is a plus here, I cannot conclude that the answer, for example, must be 0 plus because there is plus. So it's possible that here we have plus and here we have minus. So in this thing, we already established it last time. So now let's see for this case, what is cos pi half plus? So this is the unit circle. And then this is theta equals 0. And this is theta equals pi half. And pi half plus means a little bit after pi half, which means here. So this is pi half plus, a little bit after pi half. Okay, it seems the screen is freezed. Just 1 second. Maybe I have to stop share and share again. Yeah. So this is theta equals 0. Pi half, we have to move counterclockwise. That's the positive direction. And this is pi half. Pi half plus means a little bit after pi half. So a little bit after pi half would be some point around here. And cos means the x value. So x value here is close to 0, but a little bit less than 0. So this is on the negative part or side of x-axis, because you know the left side of x-axis means negative side. So It's a little bit less than 0. It's a small negative number, small negative number. So the answer is going to be 0 minus here. See figure below. So 1 over 0 minus, and last time we saw that this is minus infinity. See the notes from last lecture. One over 0 minus means minus infinity. We said a positive number over 0 minus will be minus infinity. Okay, so this limit tan x, so we could not use the theorem here, but instead we could analyze the situation and use the rule that we mentioned from last time, that the constant positive number over 0 minus will be minus infinity. So this limit is minus infinity. Thus, we can say that x equals pi over 2 is a vertical asymptote for y equals tan x. So if the right limit or left limit are minus infinity, then we can say that x equals that number is a vertical asymptote. Okay. And so this is for tan x. Now, next, we want to compute limit sine x over x as x approaches to 0. So let's see, this is a very famous limit, maybe the most famous trigonometry limit in calculus is limit sine x over x. I'm sure many of you have seen this maybe in high school, and you know that the answer is 1. So let's see how we can show that the answer is 1. So first of all, we can try to replace x with the number. What do we get? So limit sine x over x, x approaches to 0. So this is 0 over 0. Sine 0 is 0, and x at 0 is 0. And 0 over 0, last time we saw that 0 over 0 is indeterminate, is an indeterminate form. And we need to simplify to compute this limit. So to simplify, we saw that if you have an indeterminate form, the answer could be potentially anything. Could be 5, could be 10, could be 0, could be infinity, depends on the example. Now to simplify, we saw that if, for example, we have polynomials, we can try to factorize. If we have square roots involved, we can try to rationalize, etc. But this one is neither a polynomial nor square root function. So we have to simplify using another method. So we will use geometry to compute this limit. Along with a theorem called squeezing theorem. So we need two things. So simplifying this, in other words, is more complicated than the examples we saw last time. Last time we just simply factorized or rationalized. But here we have to use geometry and also a theorem called squeezing theorem to compute this limit. So first of all, let me state the squeezing theorem. Squeezing theorem. Let f of x, g of x, and h of x be three functions. Three functions such that f of x is less than equal to g of x, and that's less than equal to h of x. For all x close to some number a, also suppose that limit f of x and limit h of x, suppose that these two limits exist and equal to some number L, and for some real number L, then we can say that limit g of x as x approaches to a exists and is equal to L as well. So let me draw a picture for you to show what happens here, what's happening. So that they have three functions, and okay, so let me so let's say this is so this above function, let's call it h of x. Middle function, let's call it g of x. Below function, let's call it f of x. Okay, so we have three functions, f of x, g of x, h of x. Now the middle function, so the above and below functions, both of them at some point A have limits and their limits are equal, right? See, h of x is the above function, then we have g of x, the middle function, f of x is the below function. Now, above function and below function, both of them, the limit is equal to L. For both of them, limit is equal to L at A. Then the middle function, which is squeezed between above and below function, must have the same limit, must have limit L again. Right? So this is squeezed, or sometimes we say sandwich, between two functions, and the above and below function have the same limit, and this is squeezed between them. So if the above and below function are the same, have the same limit, the middle function must have the same limit. Same limit L. The limit of the middle function exists and is equal to L. So this is not obvious, needs a proof, of course. We will skip the proof. But I can give you the idea of this theorem, that what this theorem is about. So for example, let's say for numbers, this is obvious. So if let's say if I delete the limits from this theorem, then becomes almost obvious, because let's say if you have three numbers, let's say A, B, and C, and I say that A is less than equal to B, B is less than equal to C, right? So you have a smaller function, then middle function, then higher function. And if I tell you that A and C are both 5, let's say, you have three numbers. the smallest and the biggest number, both of them are 5. Then the middle number, which is squeezed between these two numbers, must be also 5. If the smaller and the bigger functions are 5, both of them, middle number must be 5 as well. So for numbers, it's obvious, but for functions and limits, it's not obvious. It needs proof, but we skip the proof. But I want to tell you the idea that why this happens, that if a number is squeezed between two others, smaller and bigger one, and the small bigger one are the same, the middle one must also, the limit of the middle one must also exist and is equal to the same number. Okay, so this is a theorem, important theorem in the concept, in the limits or concept of limit, topic of limits, which is called squeezing theorem. Now, remember I promised you that I'm going to calculate this limit using geometry and squeezing theorem. So this is squeezing theorem. Now, what do I mean by using geometry? Now, let's use this theorem and the following geometric argument to compute limit sine x over x as x approaches to 0. So first, suppose that x is bigger than 0, i.e. we want to compute the right limit. Remember, to calculate the limit, we have to calculate the right limit and left limit. And if both of them are equal to the same number, then we can say that the whole limit exists and is equal to the same number. Okay, now I want to compare 3 areas here. So in figure above, we can say that area of the triangle OAB is less than area of sector OAB of the circle. And this is less than area of the triangle OA prime B. So I'm comparing areas of 2 triangles and 1 sector of the circle. Okay, so OAB, as you can see in this picture, OAB here as a triangle, the area is less than OAB as a sector, right? Because see, for sector and the triangle, the difference is in this small region here. See this small region I'm showing with the cursor? If this small region is included, then you will have the sector OAB. And if it's not included, then you have the triangle OAB. So the triangle OAB is less than sector OAB, and the sector OAB is less than the triangle OA prime B, which this triangle, which definitely includes both the other triangle and also the other sector. So the area of this is the biggest one. Okay, now the area of, okay, now let's calculate. The area of OAB is 1/2 times OB times AH, right? The area of triangle 1/2 times base times height, less than area of the sector is 1/2 times the angle, which is x, times the radius squared. Radius here, I'm assuming, is 1. This is a unit circle, because you know that all the trigonometric functions are defined with the unit circle, or inside the unit circle. So this is the unit circle. So OB is equal to the radius, which is 1. And then we have the area of OA prime B, which is 1/2 OB times A prime B. Now OB is 1, as we said. What about AH? OB is the radius, which is 1. AH is how much? See, if you want to find, if you remember in the first lecture, I reminded you that for finding sine and cosine of an angle, first you need to find the angle, then find the point on the unit circle, and then the y-coordinate of this point, which is AH here, is considered as sine x. The x value is considered as cos x. So here y value of this point A is considered as sine x. So AH is sine x. So this is 1/2 times 1 times sine x less than 1/2 times x. And this one less than 1/2 times OB is 1. A prime B, how much is A prime B? So this axis here, which is parallel to y-axis, as you know, is called tan axis. You also reminded in the first lecture. So this is called tan axis, and this distance here will be tan x. So when you have the tan axis, the distance from the point where you extend the radius, you extend it until you hit the tan axis. Then from that point to B here, which is the starting point, will be tan x. So A prime B is tan x by definition of tan of an angle. So this is 1/2 times 1 times tan x. So I can say that 1/2 sine x less than 1/2 x. And this is less than 1/2 tan x. Now, how about if I divide everything by sine x? Then I get, and divide by sine x, divide by 1/2 sine x. Then what do I get? I'll get 1 less than x over sine x less than tan x over sine x. And this means 1 less than x over sine x. Tan x over sine x, tan x itself is sine x over cos x. Then divided by sine x, I'm going to get 1 over cos x. Okay, so now see, I have a middle function which is squeezed between two other functions. So I can use squeezing theorem. I can use squeezing whenever you have one middle function squeezed between two other functions, as long as the two other functions, smaller one and the bigger one, has the same limit, then you can say that the middle one must also have the same limit. Now remember, we are calculating the limits as x approaches to 0 from right. X approaches to 0 from right. So what will be the limit of the smaller and the bigger functions? So let me say, as x approaches to 0 from right, we can say that the limit 1 as x approaches to 0 from right, this is definitely 1, right? Because it's a constant function. The limit of a constant function is always the same. And what about cos x? Limit 1 over cos x. x approaches to 0 from right, this is 1 over cos 0 plus, which is 1 over 1, and that's 1. Cos 0 is 1, right? Because it's a fraction, limit of top exists, limit of bottom exists, and limit of fraction therefore exists. And because limit of bottom is non-zero, we can just write the limit of the fraction as limit of top over limit of bottom. So limit of a fraction, we saw this last time. Limit of a fraction is limit top over limit bottom as long as limit bottom is non-zero. Here limit bottom is 1, which is non-zero. So we can write it this way. So by squeezing theorem, limit the middle function, which is x over sine x, x approaches to 0 plus, exists. And how much is the limit? And the limit x over sine x as x approaches to 0 from right is equal to 1. Because the small and bigger function have the limit 1, so middle function must also have the limit 1. Okay, but remember we wanted to find limit sine x over x. The goal was to find limit sine x over x here, but we found limit x over sine x. So what is the relation between limit x over sine x and limit sine x over x? The relation or the connection is straightforward. Hence, we can say that limit sine x over x is equal to limit 1 over x over sine x, right? Sine x over x is same as 1 over x over sine x. And now I get limit top over bottom. Is limit top, which is 1, over limit bottom, which is 1. Limit top over bottom is limit top over limit bottom as long as limit bottom is non-zero. You can also mention here because limit bottom is 1, which is not 0. So we can say limit top over bottom is limit top over limit bottom, and this is 1. So limit sine x over x as x approaches to 0 from right is 1. Where x as x approaches to 0 from right is 1. Now for the other limit, now for limit sine x over x, x approaches to 0 from left. So we have two approaches, possible approaches for this. We can either do it from the scratch, because right now the picture that we did was a positive angle, right? Because remember the counterclockwise is positive direction. We could do that from the scratch, but this time we have to sketch it clockwise and do all the same argument again. But the easier way is to use the results, because we already showed that limit sine x over x, x approaches to 0 plus is 1. So if in some way we can use this result to find this limit, well, that would be great. We already have this. So if we can use it to find this, that would be great. So how can we do that? Well, we can use a substitution here. Sometimes, substitution is a method that, can help you to relate two different quantities. So here, right limit and left limit. Or in integration, you can use substitution, to simplify the integration, simplify the expressions. Or today I was teaching differential equation course, and that one again, you can use substitution. So here, if I call x, so for this, use the substitution let's say x equals minus t. So when you use substitution, let's say if you want to convert, let's say you have a limit in terms of x, you want to switch from x to t, for example. Then you have to rewrite everything in terms of t. So rewrite the whole limit in terms of t. Okay, so right now, see the function is in terms of x, and here I also have x approaches to some number, right? So I have to replace this expression with t and also this whole expression in terms of t. So do not forget one of them. So everything when you use substitution, same thing for integrals. So when you use substitution, you want to switch from x to t. All the x's must be converted to t. If you have some x's and some t's, the mixture, then that's not acceptable. Okay, so if you want to go use substitution, convert x's to t's, all x's must be replaced in terms of t and vice versa. Okay, so first of all, x approaches to 0 from left. So that means minus t approaches 0 from left. So t itself must approach 0 from right. You want 0 minus means what? Means a little bit less than 0. If you want minus t to be a little bit less than 0, t itself must be a little bit bigger than 0, right? If t is a little bit bigger than 0, like 0.1 or 0.01, then minus t will be a little bit less than 0, like minus 0.1 or minus 0.01, and so on. So t approaches to 0 from right. And so we can say that limit sine x over x approaches to 0 from left is equal to the limit sine minus t over minus t as t approaches to 0 from right. So sine minus t is minus sine t. So we can write this one as limit minus sine t over minus t. T approaches to 0 from right. And then cancel minus with minus. So I can write this one as limit sine t over t. T approaches to 0 from right. And then this is 1. Because we already showed that limit sine x over x approaches to 0 from right is 1. We already showed this, right? So we can say that, and this is the same limit, right? This is the same limit, just instead of x, t is appeared, but it's of course the same limit. So if this is 1, this has to be 1. So what did we show? So we showed that limit sine x over x as x approaches to 0 from right is same as limit sine x over x approaches to 0 from left. Both of these are 1. So if both right limit and left limit are 1, then we can say that the whole limit is also 1. The whole limit exists and is equal to 1. All right, so let's look at an example. Find limit sine 3x over x as x approaches to 0. So let's sine x over x, we know it's 1. Now I want to find limit sine 3x over x. So how can we do this? So we can rewrite this. We just need to usually for this type of question, we need a small trick. So we can usually divide and multiply by a number or something like that. Just use a small trick to find the limit. So I can write this one as limit. So sine 3x over x. If it was sine 3x over 3x, then of course I could use this formula, because if you want to use this formula, this angle here must match with this angle. So if it's x, this should be x. If it's t, this should be t. If this is 2t, this should be 2x. If this is 3x, this should be 3x, and so on. So I can write this one as limit sine 3x over x as x approaches to 0. I can write this one as limit sine 3x over 3x as x approaches to 0, and then times 3, right? Basically, I've just divided and multiplied by 3. Of course, I'm allowed to do that, right? When you divide and multiply by 3, means basically you're multiplying by 1. And multiplying by 1 is allowed. It's okay to multiply with 1. So now if I replace 3x with t, so use t equals 3x. Again, remember, when you want to use substitution, convert from x to t, everything must be switched to t. So here I have x approaches to 0, so that I can conclude that t approaches to 3 times 0, which is also 0. T is 3x. So if x approaches to 0, t approaches to 3 times 0, which is 0. So I can say that limit sine 3x over 3x, x approaches to 0 times 3 is equal to limit sine t over t, t approaches to 0 times 3. And this one we already know it's 1. So 1 times 3, the answer is 3. Another example, let's say find limit sine 4x divided by sine 5x as x approaches to 0. So again, remember this type of question, usually the trick is divide and multiply by something, right? So what could we do? We know sine x over x, we know the limit. So right now there is no over x, but I can divide and multiply by x basically, right? So I can write this one, this limit as limit sine 4x over sine 5x. I can write this one in the form sine 4x over x divided by sine 5x over x. Right, so it's just basically dividing and multiplying by x here. Sine 4x over x divided by sine 5x over x. Right, and divide and multiply by x means just multiplying by 1, which is allowed. But here I have 4x, so if I want to use the limit sine, basically t over t is 1, this angle here must match with this one. So this is 4x, but this is x. But again, I can solve this issue. I just need to divide and multiply by 4. So I can write this one as limit sine 4x over 4x times 4 divided by sine 5x over 5x divided multiplied by 5, right? So I divide and multiply numerator by 4, and denominator also divide and multiply by 5. X approaches to 0. And then this is 1 times 4 divided by 1 times 5. You can call this one t if you want, and then sine t over t, the limit will be 1 as t approaches to 0. We can call this one s, for example, if you want. Sine s over s, s approaches to 0 is also 1. Or in the exam, if you write this way, it's still acceptable, you know. Of course, you know, if you write that as sine t over t and this one sine s over s, and it's more detailed, more explanation. But this much explanation is also acceptable, you know, sine 4x over x, because the angles match. If you replace it with 1, I still accept it. I will still accept it in the exam. Because I know that in your head, basically, you replace 4x with t, and then you replace the answer with 1. So yeah, this much explanation is enough for exam as well. So 1 times 4 divided by 1 times 5, and the answer is 4 over 5. Now another example, let's say if you want to find limit 1 minus cos x divided by x, x approaches to 0. So 1 minus cos x divided by x. Well, the first thing you can try is just replace x with 0. Let's see what happens. 1 minus cos 0 divided by 0. So this is 1 minus 1. Cos 0 is 1. 1 minus 1 over 0. And this is 0 over 0. And this is indeterminate. Needs simplification. So simplification in the context of trigonometric functions. So remember, what we said, 0 over 0 is indeterminate, means the answer potentially could be anything. And we have to simplify. Now, simplifying for polynomials, we said means factorizing. For square roots means rationalizing. For trigonometric functions, normally means, you know, trying to connect it to limit sine x over x, because we know limit sine x over x is 1. How can I relate this? But right now it's cos x, it's 1 minus cos x. How can I relate it to sine x? Well, we have a connection. We know a connection between 1 minus cos x with sine of an angle. So recall that cos x can be written as 1 minus 2 sine squared x over 2. So this is using double angle formula. I reminded you in the first lecture again, just look at the notes for the first lecture. Cos x, or we said cos 2x is 1 minus 2 sine squared x. We can also write it, if you replace x with x over 2 in that formula, you can write it as cos x equals 1 minus 2 sine squared x over 2. So this means if I take cos x to the other side, 1 minus cos x equals 2 sine squared x over 2. So now let's rewrite the limit. So the limit is 1 minus cos x divided by x. X approaches to 0. So this is limit 2 sine squared x over 2 divided by x. X approaches to 0. Now let's see how we can write this. I want to use the fact that sine x over x is 1, the limit, as x approaches to 0. So I can write this one as 2 sine x over 2 divided by x over 2, right? And times 1/2. Oh, it seems the screen was freezed. Oh. Let me stop share and share again here. Okay, so we established that we need simplification, which means we have to connect it to limit sine x over x somehow. And we said we are going to use the double angle formula. Cos x is 1 minus 2 sine squared x over 2. And I said that to derive this, use the notes for the first lecture where we said cos 2x is 1 minus 2 sine squared x. Just replace x with x over 2. Then we get cos x equals 1 minus 2 sine squared x over 2. And the next step was very straightforward. We just took cos x to the other side and this term to the left-hand side and to the, we took this one to the left-hand side, this term to the right-hand side. Then we got 1 minus cos x equals 2 sine squared x over 2. So we replace this with 2 sine squared x over 2 divided by x. Remember, this is the limit we want to calculate. Now I want to write this as sine x over 2 over x over 2 times 1/2. Well, 2 is 2, right? Sine x over 2. Well, I know that I have sine squared x over 2, but just bear with me. Just one factor. I wrote one of the factors here, sine x over 2. And here over x over 2. Right, so in this x, I'm changing it to x over 2, which means basically I'm multiplying by 2, right? Because 1 over 2 is 2. So basically I'm multiplying this by 2. So if I want to make this unchanged, I have to also multiply with 1 over 2, so that this 1 over 2 cancels with this multiplication with 2. This 2 is from before, right? So this 2 is remained intact, but this one is multiplied by 2 times 1 over 2, they cancel. And then I still have another factor of sine x over 2. Because this was sine squared x over 2, I used one factor here and one factor here. And the rest I explained. So this is just a simple high school algebra that if you multiply this with this, divide by this, times this, you get this expression. It's just a simple high school algebra. I just rewrote it this way. X approaches to 0 here. So here now sine x over 2 over x over 2. Again, if you want, you can call x over 2 as t, sine t over t. T approaches to 0, it's 1. So this is 2 times 1 times 1/2. And this one will be sine 0 over 2. Remember we said for trigonometric functions, we can just replace x with the number. Also composition of trigonometric function for a nice function, which I said formally I will state it later as a theorem. But for now, I explained to you that, for not only for sine x itself, also for sine x over 2 or for sine 2x, etc., you can still replace x with the number. But I will state this theorem formally later. But for now, just let's replace x with the number. We get sine 0 over 2. So 2 times 1 times 1/2 is 1 times sine 0 over 2 means sine 0, which is 0. And 1 times 0 is 0. So we showed that limit 1 minus cos x divided by x approaches to 0. This is 0. Okay. All right, now let's look at the next example. Limit 1 plus cos x divided by x approaches to 0. So this one again, so previous example was 1 minus cos x divided by x approaches to 0. So we replace x with 0, top and bottom, we got 0, 0 over 0 needs simplification. Simplification in this case, we said, means, trying to connect with limit sine x over x. But here, when we replace x with 0, what do we get? We get 1 plus cos 0 divided by 0. So this is 2 over 0, which is not indeterminate. So this is the important difference with the previous example. So all the complications and simplifications arise where you have an indeterminate form, for example, 0 over 0, and the answer potentially could be anything. You want to find out what. But if you have 2 over 0, well, 2 over 0, we know the answer. A positive number over 0, if it's 0 plus, positive number over 0 plus, plus infinity, positive number over 0 minus, minus infinity. So here we can say that limit, the right limit, 1 plus cos x divided by x. This is 1 plus cos 0 plus divided by 0 plus. This is 2 over 0 plus, which is plus infinity. And the left limit, 1 plus cos x. This is 1 plus cos 0 minus over 0 minus. This is 2 over 0 minus. This is minus infinity. So the right limit is plus infinity. Left limit is minus infinity. And the whole limit does not exist. Even the one-sided limits still do not exist. Remember, we said that if the limit is infinity or minus infinity, so still we call that limit does not exist. So right, even one-sided limits do not exist. Neither of them exist. The one-sided limit, and of course the whole limit does not exist either. And the next example, limit cos x divided by x minus pi half. X approaches to pi half this time. Previous examples, x approached to 0. This time x approaches to pi half. Okay, so let's replace x with pi half first. Let's see what happens. So we get, if we replace x with pi half, we get cos pi half divided by pi half minus pi half. And this is 0 over 0. Again, indeterminate. Needs simplification. So what type of simplification do we need here? Remember, we try to connect it to sine x over x, but right now, and remember, if you want to try to connect it to limit sine x over x, x must approach to 0, right? Limit sine x over x as x approaches to 0 is 1. Right? So limit sine x over x, for example, let me also mention this, limit sine x over x, x approaches to 0 is 1. But let's say if you have a limit sine x over x, x approaches to, I don't know, pi half, for example. So then this is sine pi half over pi half, which is 1 over pi half, and this is 2 over pi, right? Because for pi half, when we replace x, for 0, when we replace x with 0, we got 0 over 0, which was indeterminate, and we needed some tools to develop to calculate the limit. But for pi half or for any other number other than 0, you will not get 0 over 0. So you can just replace x with the number and calculate your limit. Okay, so that's a very common mistake. I remember that people think limit sine x over x is always 1. No, limit sine x over x as x approaches to 0 is 1. And normally what I was saying here is that to calculate 0 over 0 limits, we will have to connect it with limit sine x over x as x approaches to 0. But here x approaches to pi half. So how can we solve this issue? We can use substitution. So use substitution. Let's say t equals x minus pi half. So t equals x minus pi half, then as x approaches to pi half, t will approach to 0, right? T is x minus pi half. So if x approaches to pi half, t will approach to pi half minus pi half, which is 0. And now we can try to rewrite the limit in terms of t. Right now it's in terms of x, and every x must be replaced with t, including this part here. So this part, we said that, established that it will be replaced with t approaches to 0. What about this part? So t is x minus pi half. So how much is x in terms of t? T is x minus pi half. So x is t plus pi half. So then we get limit sine cos x is t plus pi half. So limit cos x over x minus pi half, x approaches to pi half is equal to limit cos x we said is t plus pi half, x minus pi half. So x is t plus pi half. So t plus pi half minus pi half, and t approaches to 0. Now cos pi half plus t is how much? Cos pi half plus t is minus sine t. See lecture 1. Right, in lecture 1, I reminded you about these identities that you originally learned in pre-calculus. So this is minus sine t. So we can say this limit is limit minus sine t divided by denominator. What is denominator? T plus pi half minus pi half is t. T approaches to 0. And this limit is minus 1. Right? Limit sine t over t approaches to 0 is 1. So this limit is minus 1.